And now it's time for the last talk in this session, and it's also on backscatter networks. And the talk will be given by Wei-Guo Wang, who will talk about acoustic backscatter network for vehicle body in white.
Okay, good morning. My name is Wei-Guo Wang. I'm very excited to introduce our recent work, Acoustic Backscatter Network for Vehicle Body in White. This is a joint project between NEO and Tsinghua University. Before I introduce the system, let me first explain what the body in white, or BIW, actually is. It's the bimetal frame of a car. It's made of high-strength steel or aluminum to withstanding bending, twisting, and fatigue. The BIW is crucial. It keeps the whole structure rigid. It protects the passengers in a crash. For electrical vehicles, it also used to shield the battery pack. In short, BIW is crucial. BIW is the backbone of the car, and if it breaks, everything else is at risk. Even though the BIW is built to last, but it can and does degrade over the time. Fatigue, cracks, corrosion, and even underbody impact all can weaken the BIW. And in real case, cause the battery fire. And the scary part is that it often happens with no warning sign at all. So, can we monitor the structural health of the BIW before it fails? Well, the first idea comes to mind, you use the wireless sensor, right? No wiring, easy to install, sounds perfect. But here's the problem. The BIW actually acts like a Faraday cage. It blocks the radio signal. You can't simply communicate reliably with the sensor inside. And it gets worse. Most wireless sensor relies on the battery, but the vehicle have a long lifespan, often over a decade. This battery won't last forever, and they need to be replaced at some point. But once the sensor is installed inside the BIW, replacing its battery is expensive and impractical. Well, while the sensor comes the problem too. First, modern cars already have over 3 kilometers of wiring, and even more just makes things messier and increase the risk of interference. Second, wires add the weight. And in electric vehicles, the actual weight means it will directly impact its driving range and energy efficiency, and of course, its acceleration performance. Third, it's expensive. You need durable, heat-resistant cables, and installing them, that is a lot of labor cost, which inflates the manufacturing costs. In the end, why the sensor just impractical either, especially for electrical vehicles? Actually, this is not a theoretical concern. The whole industry is making big changes. Let us take a Tesla as example. Back to 2012, Model S used around 3 kilometers of wiring. 5 years later, Model 3 cut that in half. Cybertruck, released 2 years ago, used less than 1 kilometer of wiring. That is 2/3 reduction in just a decade. And Tesla isn't alone. The whole auto industry is moving towards the lighter, simple design, of course, including NEO. This means that there's less access room for the wide solution. So the problem is very clear. Wireless fails, wired doesn't scale. Both approaches are fundamentally misaligned with the BIW. And so maybe the problem isn't how to fight the BIW. It's time to find the solution that works with BIW, not against it. This is exactly what we do with our system, AracNet. We treat the whole BIW as a whole vibration medium. A medium carries the information. A medium carries the energy. We send acoustic waves through the BIW. These waves power up small battery-free tags placed at the key structure points. And to communicate with the tag, simply reflect and modulate the vibration using a technique called acoustic backscatter. So the BIW, which used to be a problem, now become a channel itself. So let's take a closer look at how we actually use the vibration for energy harvesting. The key is the reader transmits acoustic waves through the BIW. This vibration travels around the metal structure and reaches a special transducer called PZT attached to the tag. And the BIW vibrates, the PZD converts this vibration into the electrical energies. That energy is stored by the energy harvest circuit. And once it crosses the threshold, the tag wakes up and starts working. We also use the vibration for communication. When the tag is powered up, it listens to the vibration coming from the reader, and to send the data back, it simply modulates the reflection of that vibration. When the circuit is closed, the vibration is absorbed. When it's open, it reflects back. That's how we encode the bits using just one transistor. This is also called acoustic backscatter. And it's extremely low power since the tag never generates its own signal. Here's a quick look at our hardware design. The tag is building on well-established principle from the backscatter community, combining energy harvesting, envelope detection, and impedance control. We built a full protocol shown here, including a custom data board, a control board, and a sensor interface. The entire system can run completely battery-free. On the software side, we designed a full interrupt-driven architecture to minimize the power consumption of the CPU. The tag stays in a deep sleep most of the time and only wake up when it detects a downlink signal. In a downlink, each vibration triggers a short wake up where the CPU reads the timer and then go back to the sleep. For uplink, the timer counts down and tortures the transistor to modulate the reflections. With this design, we reduced the CPU power by over 80%. Here's our packet design for our system. We use two lightweight packet formats, one for uplink, one for downlink. In the uplink, each tag sends a 32-bit packet, which includes a short preamble, tag ID, sensor data, and a CRC. The downlink is simple, just 10 bits, a short preamble plus 4-bit command. We want to point that the most important is that we didn't include tag ID in the downlink. The reader simply broadcasts, and each tag decides locally whether to respond. Why no tag ID? As I introduced in the software side, because listen to the downlink consumes energy. The tag has to wake up and decide whether downlink, whenever a downlink signal appears. So to keep tag responsive while still conserving power, the downlink must be as short as possible. This minimum design keeps the things ultra simple and ultra efficient, which is essential for the battery-free operation. And this compact packet design lies the foundation for our low-power protocol I will describe next. But let me first take a step back and explain why coordinating tags is so hard in our settings. First, not all tag transmission packet at the same rate. Some tag used to monitor the battery, it should transmit more frequently. Some tag used to monitor the structure health, it can transmit in a low frequency. So we need to support a diverse transmission rate. Second, collision is the real problem. Due to inherent limit of the backscatter communication, we have a very long packet length. Each uplink packet length lasts around 200 milliseconds. With many tags in the network, the chance of collision goes way up. And the third, as we described in the packet design, we have very limited feedback from the downlink. The downlink packet is only 10 bits long, and to save power, we didn't include the tag ID. That means the reader cannot talk to any individual tag. It can only give short broadcast feedback, like ACK and NAICK. Together, these challenges make our coordination especially tricky. Let's start with the basic design. Each tag is assigned with a transmission period, say once every 2 slots or every 4 slots. With that period, it chooses a transmission offset. Basically, which slot in a cycle it should transmit. As long as the total channel utilization stays below 1, we can guarantee a collision-free scheduling as shown in the table. This gives us a clean and deterministic way to handle diverse transmission rate. But here's the problem. This simple design relies on one key assumption, that is, all tags are perfectly synchronized in slot. But in reality, that is hard to guarantee. Some tags might miss the beacon, the downlink packet, and some might tag need more time to charge to join the network. When that happens, their timing just doesn't line up, and that would lead to collisions. So we need a protocol that doesn't rely on tight synchronization, but can still help tags find the collision-free slots by themselves. To address these challenges, we propose a dynamic feedback protocol that helps each tag find a collision-free slot without requiring tight synchronization. Each tag is started from the migrate state, and it picks up a random slot and give it a try. If it gets an ACK, it moves the settle. If it sees the NACKs, it tries again with a new offset. Even in the settle state, the tag still needs to monitor the feedback from the reader. If it receives multiple NACKs, it goes back to the migrate. This approach is extremely simple but effective. And more importantly, this simplicity makes it a perfect fit for the ultra-low power battery-free tags. Although this protocol is simple, but we can formally prove that it always converges. This system actually can be modeled as an absorbing Markov chain. This means that from any initial state, the network will eventually reach a stable collision-free state with probability 1. We deployed our system Arachnate on the body in white of the Envoy L60, 乐道 L60. In total, we placed 12 tags and 1 reader across the BIW, covering 3 main areas: the front row, the second row, and the cargo area. We measure the energy efficiency of our tags. Depending on the placement, the tag can be activated from scratch in as little as 5 seconds, and at worst case within about 1 minute. Once charged, the tag operates as just 10 microwatts. This efficiency is crucial for substantiating operation with limited harvest energy. We evaluate the communication performance across different bit rate. For uplink, with the 375 bps at default, it provides the reliable communication across all tags with minimum packet loss. For downlink, things are a little different. We start to see a significant increase in packet loss at 1 kilo and 2 kilo bps. But this is not due to the poor signal quality. It is actually caused by our hardware limitation in the low and unstable clock on our CPU. This is by design to save the power. So we use 250 bps for the downlink to keep communication reliable. Finally, we evaluate how well the protocol performs over time. We maintain over 81 slot utilization, which is very close to the theoretical upper bound. Even when downlink packet loss disrupts synchronization, the system can quickly adapt and recovers. So overall, our protocol is stable, efficient, and self-healing. Okay, that's all. Thank you.
Thank you all. We have time for 2 or 3 questions. Okay, I have some question. Do you have any intuition how your protocol scales with more tags?
You mean more tags?
Yes. Or how many tags do we need for a car? And
okay. Actually, there are 2 problems. How many tags we need for the monitor structure health, and how protocol performs under different when we change the number of tags, right? Okay. Actually, there is a special design in the car that is there are some key structures. It will look performance like the fuel. It means when it crashes, some key structure will collapse first. So we only need to deploy the tag on that key structures. That is enough. Like 10 to 20 is enough to monitor the structure health.
Yeah, but you also wanted to maybe monitor battery, and you said that there is different frequency or latency requirements from the different tags. So when you maybe have a full vehicle deployment, so how many tags do you foresee? I mean, in addition to these structural tags.
Sorry, how many tags?
How many additional tags, I mean, for the battery and for other vehicle services? Because the idea is to replace most of the cables. Mm-hmm. So you maybe use more tags to collect maybe more telemetry from different vehicle components.
I believe the 4 to 5 batteries are enough to monitor the battery, and for the structure, 10 to 20 is enough.
Okay.
Yeah.
And the other question I had, like when the car, I mean a typical car runs maybe 20, 30 years.
Yeah.
Is there some issue, I mean, maybe for cables, for 20 years is not maybe a problem, but for do you foresee some problems for these tags because they have to be adhesive to the vehicle body, and maybe aging? I don't know. Is there maybe is there some issue over time, like in degradation in performance, or?
Actually, we more focus on the battery free. We believe when there's no battery requirement for the battery, the node can last at least can last forever, at least in the term of the battery and oil energy. But it's the node itself, the material might also degrade over time, but we didn't test that.
Okay.
Hello, here one question.
Yes.
Yeah. So here you use the acoustic signal for the sensing and also the communication, right? So for the dual purpose.
We currently focus on the communication and networking, not the sensing. But we actually deployed we will provide a sensor node that can it include the sensor interface. You can add the sensor on demand. In demand.
All right. So in that case, you deploy those tags to sense some data, and then use the acoustic communication to transmit the data back. All right. Yeah. I see.
Yes. Thanks for your nice talk. And I have a quick questions about this part. So in this paper, we like to detect the health about the body in white of a car, right? So before this excellent work, we have any other methods to detect this health for this body in white?
Your question is there any other method to
monitor? Yeah. I mean, my question is about, do we have any other methods to detect this health?
But
because I think this can complement with other methods, and then because we think this is a safety issue, right?
Yeah.
So this is very important. So why do we not just combine all these methods together and achieve a high safety for the drivers, right?
Yeah. So your question is there any method to monitor structural health?
I mean, before this acoustic method, do we have any other methods to detect the health of the body in white?
You mean? So your question is, are there any sensors or?
No, I mean before, we use the acoustic to detect this health, right? So, so before this, how can we detect?
Acoustic for communication, not for detect the health. To monitor the health, we didn't use that. Yeah.
Okay. Thank you.
Okay. Thank you very much for your talk. Let's thank you again, the speaker. And this was the last talk in the session, so let's close the session. Thank you all for your attendance, and see you all at the coffee break.